students, we are starting this channel for the students who don't have access to classes because of the lockdown of the schools. Here in this channel we will be discussing physics of class 11 and 12, and students of cbse board, ICSE board and even West Bengal board can refer to this channel for physics class of class 11 and class 12. Together with the physics class, we will even discuss quantitative aptitude of competitive examination. Here we will be discussing from the easiest to the hardest questions that are asked in the quantitative aptitude, and we will even see the easiest and the shortest tricks to solve them. In this class, we will discuss class 11's topic, that is elasticity. Okay, so let's start our class, that is elasticity. Okay, let's talk about elastic substances. Suppose if we take this rubber band, we know that it is elastic, right? That means it is stretchable, right? That means now if we stretch it and if we leave it, what kind of property does it have? If we stretch it, we see that it gets deformed, and when we leave it, it will regain its original shape. That property by which this rubber band tries to regain its original shape is called elasticity. Okay, so here when we are applying force, it is getting deformed. This object is getting deformed. So the force that we are applying is called deforming force. Okay, and when we remove the deforming force, it will regain its original shape and size, and because of the property of elasticity. Next example, as you can see in the slide, that is eraser. When we use it, when we twist it, we see that it gets deformed, its shape changes, and when we remove the force, it will regain its original shape and size. Another example also we can think of is cushion. For example, when we apply some force on the cushion, it will get deformed, it will get squeezed, right? And when we remove the force, it will again regain its original shape and it will return to its original size. Okay, and this it will do that because of the property of elasticity. So here in elasticity, what we do is we apply some deforming force on the object, it gets deformed, and when we remove that deforming force, it will return to its original shape and size. Okay, so let's see the definition of elasticity. Elasticity is what? It is a property of the body by virtue of which it regains its original size and shape after the removal of the deforming force. Is it clear? When we apply the force, the object gets deformed, and when we remove the force, it will regain its original size and shape because of the property which it has, which is called elasticity. Let's see some of the examples here. Here we have different types of elastic body. One is perfectly elastic, another is partly elastic, and the third one is perfectly plastic body. Let's first discuss about perfectly elastic body and partly elastic body. Here, for example, if we take two objects, suppose we have one object here and another object here. Suppose if you apply the deforming force to this first object, suppose it gets squeezed in this way, its shape changes, and when we remove that force, suppose it will regain its original shape and size perfectly. Then that is called perfectly elastic body. But in our day-to-day life, mostly what we see is, suppose this is a cushion, when we apply the force, it gets squeezed, for example, in this manner. Okay, and when we remove the force, it will try to regain its shape and size, and we see that it does not completely regain its original size. Suppose it returns to this form, not completely, then this kind of object is called partly elastic body. Most of the bodies that we see in our day-to-day life are partly elastic, not perfectly elastic body. And the example of perfectly elastic body is quartz fiber. That is, when we apply the force on a quartz fiber, it will get deformed, and when we remove the force, it will completely regain its shape and size. Okay, now let's see the second one, that is perfectly plastic body. Example of it is chewing gum and atta balls. You might have played with this board. If we consider this atta balls, okay, if we apply some force on it, we see that it gets deformed. Okay, if we stretch it, and when we remove the force, what we see is it will remain in the shape. It will not regain its original shape. That means here it does not have elasticity. That means it is perfectly elastic body. Okay, so here we have discussed different kinds of elastic body. For example, rubber band, and we have discussed eraser, then we have discussed cushion. Okay, and all the solid objects that we see, they are even elastic. Okay, but you all have seen already in the previous chapters maybe that solid objects, some of the solid objects are rigid. Okay, let's see, are they perfectly rigid or not? Okay, in reality, are all the solid objects perfectly rigid? Okay, so let's recall what rigid body is, what you all have studied. If this is a rigid body, for example stone, okay, it is a rigid body, right? It is made up of very small minute particles. Suppose if we consider only two minute particles, this and this. Okay, these two particles. What is the property of a rigid body? Distance between these two particles are fixed. Even if we move this stone, the distance between these two particles will not change. Even if we rotate it, the distance between those two particles will not change at all. That is the property of a rigid body. Now let's see whether this copper rod is rigid, perfectly rigid or not. See here, if we apply some force on it and will try to stretch it, if the force is large enough, what we will see is it will get stretched. That means it will become thinner and thinner, and we can get a wire of this manner from this copper rod. That means here the distance between the particles are changing, so these copper rods are not perfectly rigid. That means we see that solid bodies are not perfectly rigid and they are elastic. Let's try to understand why are these solid bodies elastic with the help of a model, which is spring and ball model. Okay, solid, we know that it is made up of large number of atoms which are placed together because of the intermolecular forces. Okay, and here we'll try to look these atoms like these balls, and these balls are attached with each other with the help of a string. Okay, so we'll consider solid to look like the spring and ball model. Before going into this, let's try to recall what is the property of a spring. Okay, let's change the color. Okay, what is the property of a spring? Here, if we apply some force on it and we compress it, what we know is its potential energy increases, right? And because of this potential energy, it will again regain its original configuration. It will come to its initial stage, and it will try to have minimum potential energy. Now, if we just stretch it, again what happens? its potential energy increases, right? And because of this potential energy, some restoring force acts on it and it will try to regain its original shape and configuration. That means whether if we squeeze it, compress it, or we stretch it, in both the cases, its potential energy increases and it will try to regain its original shape by decreasing its potential energy. Okay, now let's see here what happens. Suppose we apply some force on this atom in this direction. That means now suppose the atom moves in this direction and the distance between these two atoms decreases, right? That means here in the equilibrium position, suppose the distance between these two atoms were r0, that is here in this case. Here the net force acting on it is 0 at this position, and when we apply some force on it and because of which the distance between them decreases, that means r becomes less than r0, there will be some repulsive force acting between these two atoms. That means when this distance decreases, then r0, that means in this region the force acting on it is repulsive. Force acting is repulsive. That means now there will be repulsion between these two atoms, and because of which it will try to regain its original position. It will return to its original position, which is the position of minimum potential energy. Okay, now again if we apply force in the opposite direction so that it gets stretched, that means here the distance between the atoms will increase. That means here r becomes greater than r0. Okay, that means when the distance between the atoms increases, what we see here is that when it is greater than r1, the force becomes attractive. Force becomes attractive. That means there is attractive force between these two atoms, because of which again it will return to its original position. Okay, that means when we deform this solid object, if it gets compressed, there is repulsive force, and if we stretch it, there is attractive force, because of which now it will return to its initial position, which is the position of minimum potential energy. So we have tried to explain the elastic behavior of solid with the help of the ball and spring model, and we have seen here that atoms occupy the position of minimum potential energy. Okay, so till now we discussed what is elasticity. That is, elasticity is a property by which the object, it will regain its original shape and size after the removal of deforming force. And most of the objects, solid objects that we see, they are elastic and they are not perfectly rigid. Okay, and atoms, they occupy the position of minimum potential energy. Okay, now let's go to the next slide. Let's consider the copper rod of length L. Okay, now we'll apply some weight on it. Suppose the weight that we have applied is 1 kg. Now because of this weight, its length will get increased. That means it will get elongated. Okay, and suppose the length has increased by amount L1. So the force that we are applying is nothing but deforming force. Okay, deforming force. Now we know that when we apply the deforming force, some restoring force will be developed inside the body because of elasticity. It will try to maintain its shape, and when the deforming force is removed, it will regain its original shape. Okay, and here the force that is developed inside the body, which is opposing the effect of deforming force, is called restoring force. It is called restoring force. Okay. So here the restoring force which is developed inside the body, it will act on this area of cross section, and here suppose the area of cross section is A. Now if we divide this restoring force developed inside this body by the area of cross section on which it is acting, this ratio is called stress. Okay, so we have introduced one new term which is called stress, which is nothing but the ratio of the restoring force developed inside the body by the area of cross section. So here its definition is the internal restoring force set up per unit area of cross section of the deformed body is called stress. Okay, now let's see what its unit is. Here it is the ratio of force by area. What is the SI unit of force? That is Newton by area. What is the SI unit of area? We all know that that is meter square. So its SI unit is Newton per meter square. Now its dimensional formula. Here it is what? Ratio of force by area. What is the dimensional formula of force? Force is mass into acceleration, that is m. Dimensional formula of acceleration is L t to the power minus 2 by area. What is the dimensional formula of area? L square, that is equals to m L to the power 1 minus 2, that is minus 1, t to the power minus 2. This is the dimensional formula of stress. So let's write it here. Dimensional formula of stress is ml to the power minus 1, t to the power minus 2. So we are clear till here. Now let's move to the next slide. Here again, let's go back to the previous example. When we apply the force, deforming force on the object, here in this case the length is increasing. Okay, and the length is increasing by L1. Its original length was L. So if we divide this elongation, that means change in length, by original length, this ratio is called strain. Okay, so we have introduced a new term, that is strain. Strain is what? The ratio of change in any dimension. Here the dimension is length. The change in any dimension produced in the body to the original dimension is called strain. Okay, here what it is? Strain is the ratio of two quantities. Here in this case it is the ratio of two lengths, that means increase in length by original length. Since it is the ratio of two same quantities, it has no unit. Strain has no unit. Now we'll discuss different types of strain produced in the body. Now when we'll consider the one-dimensional figure, suppose this rod is so thin that we have to consider its length only. Here its length is increasing by L1, that means L1 by original length. This ratio, this strain is called longitudinal strain. Longitudinal strain is nothing but the increase in length per unit original length. Am I clear? Now let's go to the second type of volumetric type of strain, that is volumetric strain. From the name itself you can think this is related to volume. Volumetric strain is related to volume. For example, we consider a cubical box. Suppose we have taken this cubical box. Suppose its initial volume is V. Okay, now we'll apply some force from all the directions on all the faces of it. That means we are applying the normal force, that means we are compressing it, and because of this force its volume will get decreased. Suppose now it will become of this shape and its final volume is V1. That means what is the change in volume? That is V minus V1 if we write it as delta V. Delta V is the change in volume, and strain is what? The change in dimension by original dimension. Here we have the change is delta V by original dimension is what? V. This ratio, change in volume by original volume, is called volumetric strain. Okay, now the third type of strain is what? It is shear strain. Before we define what shear strain is, let's try to understand it with the help of an example. Let's take an eraser. Let's first draw the diagram, and let's keep this face of the eraser fixed. Okay, now we'll apply some force on this face of this eraser above surface tangentially, like this. Okay, so we are applying the tangential force on this eraser. Because of this tangential force, what will happen is this will get deformed, and this face of this eraser will get turned by some angle. That means the face which is perpendicular to the fixed face of the eraser will get turned by some angle when we are applying the deforming force here. So what is the work of this deforming force, tangential deforming force that we are applying? In this case, there is no change in length, there is no change in volume, but there is change in the shape. And here, how is the shape changing? The face which is perpendicular to the fixed surface is getting turned by some angle, and this angle by which it is getting turned is called shear strain. Okay, so now let's define it. Shear strain is the angle through which a face perpendicular to the fixed face, that means the face here shown here which is perpendicular to the fixed face, gets turned by some angle when we apply tangential deforming force on it. This angle is called shear strain. Here we have shown the 2D figure of this eraser. Now here in this diagram we have shown the 3-dimensional figure. This face is fixed and we are applying the force on the upper face tangentially, and this face which is perpendicular to the fixed face gets turned by some angle, that is theta. This theta is called shear strain. Okay, so we have discussed 3 types of strains. First is longitudinal strain. There is change in length, and if we divide it by original length, it is called longitudinal strain. Second is volumetric strain. If we divide the change in volume by original volume, it is called volumetric strain. Third one is the shear strain, that is the angle by which the face perpendicular to the fixed face gets turned under the action of the tangential deforming force, is called the shear strain.